Hey, what's up guys? This is going to be a quick video on how to work with rotary encoders. Now, all of the examples you're going to see in this video will be using the Arduino, but really you could use any microcontroller. So let's get started. Now, I'm not going to really get into the details of the pros and cons between using a rotary encoder and a potentiometer, because I'm assuming that if you're watching this video, you've already made that decision. But real quick, rotary encoder just spins forever, okay? Gives you incremental position feedback, meaning you don't actually know exactly where it is. It's not absolute. It only gives you the position of where you were previously, so in relation to where you were previously, which is why it's called an incremental encoder, and it provides digital data to the microcontroller. You can think of it like digital, but it's really not like a serial protocol communication type digital signal. And we'll get into that a little bit more. It's very easy to use. As soon as you understand what it's outputting, this will all make sense. The one I'm using here is from SparkFun. I'll put a link down below to this actual encoder, just in case you want to follow along. But I probably shouldn't have unplugged that while I had power on. But anyway, let me get this back in there real quick. Hopefully it still works. Okay. Anyway, little delay. Alright, so anyways, basically, let me show you another thing too real quick if I could get it up. Let's see if it still works. No, it doesn't. I have a program running on the computer here that I want to show you in processing. Okay, as I rotate the encoder, the line on the screen will rotate at the exact angle as the encoder. Okay, so kind of cool. Anyways, I'll get into some of that code too, but let's start talking about how this thing works, how you wire it up, and etc. Alright, so I can get this out of the way. So basically, when you look on the website, and I didn't think I was going to actually have to get into this, but when you go and look at the data sheet, they show a few wiring diagrams on how to hook this up. Basically, this encoder is kind of cool too because it has a bicolor LED and a switch, but when you push it in, it actually is like a little tactile switch. But anyways, I'm not going to get into that. I'm going to assume that you know how to wire up an LED and a switch. So the other three pins on the other side are A, C, and B, like that, okay? And they actually recommend you tie, you put a 10k ohm resistor here, you got a 10k ohm resistor here, you tie both of these to 5 volts off your microcontroller, and then basically the encoder itself is like little switches here, where you have a switch here and a switch here, and then this would be your A signal and this would be your B signal that you would wire up to, and then these would both be wired to this is pin C, but this would be wired up to your common pin on your Arduino, or ground. Okay, so basically what your output B and A will either be pulled up high, or when the switch here is closed internally to the encoder, it pulls that signal to ground. Now, who knows what is actually happening here? I don't know the specifics of what's inside that encoder. But for now, we'll just assume it's either high or low. So go ahead and wire that up, and you'll find it does not work. It didn't work in my case. Or it works very poorly. So if you keep reading on in the data sheet, you'll see that they talk a little bit about bounce on the circuit and a little bit of noise. So they recommend you still have this 10k ohm here, but then you wire up another 10k ohm here, and then a capacitor here that you also tie to ground, and then the same thing over here. which is also tied to ground. This is a 10K ohm. Now I'm not labeling these capacitors yet for a reason. This would be your A wire then, and this would be your B wire, or your B signal. Now they recommend using 0.01 microfarads, which is a 102 cap. Tried that. Works a little better. Still not great. So I decided to use 0.1 microfarad capacitors on both sides. Microfarad capacitors. That's a 104 package. 104. And it works great. So that's how I actually wired it up. And that's what this circuit is up here. It's the two 10Ks with the 0.1 microfarads going to ground. Okay? So that's how you wire it up. But now you need to understand what these signals are, A and B, and what do they mean? How do you work with them? So for this, and this is probably the most important part, we got to draw some waveforms. Okay? So let's, I'm terrible at drawing waveforms. Let's make this here A. This is your A signal, which could either be, just make a big A. So when you look at it, this could either be 5 volts or 0 volts or tied to ground, right? I showed that from the last drawing. It could be either of these two things. So as you move through time, as you rotate the encoder, you'll notice that the A signal will go from high to low, and then this just repeats. I'm only showing one period of this, or one single pulse. So as you rotate it, the period of this pulse will occur faster or longer over time. So, right now it's stopped. It could be either at 5 volts or 0 volts. I don't know. It depends on where you left it. So as you rotate it, you'll get these pulses. And the data sheet actually says you get 24 of these pulses per revolution. Per rev. Sometimes you see this as PPR or just PR. That doesn't matter. But what's funny is that this PPR value kind of is misleading, because it makes you think that you're only getting 24 pulses total of resolution per single rotation. And that's not true. And I'll get into that in a little bit. But if you just look at one channel of the encoder, which is A, you will get 24 of these rises. Okay, you'll get 24 times it'll be up to 5 volts, if that makes sense. Because over time it looks like a big square wave, and you get 24 of those in one revolution. So that's the A signal, but if you think about that, maybe you could use that for position, but it really doesn't give you a lot of information if you don't know which way you're rotating the knob, which is why we have a second channel. Because if we rotate it forward, the A signal is falling and rising, right? If you rotate it backwards, we're just moving this way now, it's still just falling and rising. So it doesn't give you any perspective on direction. You could use the A signal just for velocity feedback if you wanted to, just speed feedback. You can measure these pulses and it would give you some speed, but still you would not know direction, which is important. So the B signal, what they do with this is, let's see if I can draw this up. The B signal is exactly 90 degrees out of phase with the A signal. And again, this is only going from 0 volts to 5 volts. So this starts to get a little confusing here, but not really. It's just a square wave that's exactly 90 degrees out of phase with A. So again, at any point in time, if you measure this B pin or signal from, with reference to ground, it will be either high or low. But now that we have two of these signals here, we can actually start to figure out which direction we're going in, just based on the trigger events. All right, so let's say you're looking at all of these signals, and at any given point in time, as you're rotating it, only one of these signals, either A or B, will actually change states. You're not going to get an A change and a B change at the same time. So let's see, as you're rotating it, A signal is high, B signal is low. So you're rotating it one way now. All of a sudden you get a change on your B signal. B signal goes from 0 to high while A is high. That means you're rotating it forward. We know that. We'll put that in the code. You continue to rotate on. The A signal falls while the B signal is still high. That means we're rotating forward. Okay, and you just keep going through it, and then all of a sudden you get a change in the B signal from high to low while the A signal is still low. That means we're moving forward. So you code all this into your code so that you understand exactly which direction. And so you have all these different states that it could be in, and then depending on which event happens and what the other signal is at, you can determine direction. Because if you move the other way now, B signal is low, A signal is low. You get a change in the state from the B signal from low to high while the A signal is still low. That means you're moving reverse. So it's the same exact thing. You just keep going through it. You just move in time. Now you don't have to get so hung up on which is A and B. This could easily just be B and A up here. It doesn't matter. And if you're confused about how you're going to wire this thing up, that still doesn't matter. You could have your A and B signal completely backwards. As long as this algorithm that you write in your code is true, that these states are always here. And some people call this like gray code, where you have a 1 0, then 1 1, 1 0. You just go through it as different states. But I prefer to do it just on these events. My A signal falls. Is my B state high? Yes, that means we're moving forward. All right. So kind of try to put that into the ROM of your brain for now, because when we go to the code, we're going to have to use this exact graph, and hopefully I can pull one up on a data sheet so we can kind of go back and forth. All right. Now I want to talk about this 24 pulses per revolution. Since we have two signals and we have all of these different changes of states, we can actually increase that resolution a little bit, right? Because we have the A signal can go, if you just count here, you basically have 1, 2, 3, 4 states that this thing can happen. So there's going to be 4 events in a single period. Right? Because we're going to assume for now that this is the first event. This would be a rise in A. That's a 1 pulse. Okay? So that's one that tells us something has moved when you get that first A rise. Then you get your second event when the B signal rises. Now we're at 2. Keep moving. As you keep rotating, the A signal falls. That's your third event. Keep going. The B signal then falls. That's your fourth event. And then you keep going on and it repeats. So what you actually get is 24 times 4 events, basically. We're going to call them whatever you want to call these 4 changes of state, which gives you an effective resolution of 96 pulses. If you just measure pulses. And that's what we're going to measure. It's either a pulse high or pulse low. Okay, so you're going to notice is that as we rotate it, we're actually going to get 96, because we're going to count each one of these events as a change in state, as a pulse, and we'll count those up. So as you move the knob full 360, you get 96 pulses. Sometimes they call these encoders quadrature because of this. Okay, so anyway, that is basically how this whole thing works. We're going to wire up the A and B signals, as I showed in that circuit, into the interrupts of the Arduino, because you want to catch these very quickly. If you miss one, then you don't know, and you're going to lose your actual resolution. So let's shoot over now to the code. Alright guys, so let's take a quick look at the code here. We'll go through it line by line, make sure we cover everything in here. I may even go into the processing code here a little bit. I kind of just fumble my way through processing, so I'm not really an expert there. I usually just copy code out of other projects. This kind of gives you this effect with the line kind of going around. I might cover that. Oops, I didn't want to run it again. I also have a nice little thing here in the code to show the actual position of the encoder in the serial monitor here. And just to verify, as you do rotate it, 360 degrees, you do get 96 counts, okay? And we'll go over that a little bit and how that all works. So let's go through the code here. We start off, we initialize a few variables, no big deal. We'll cover what these do in a sec. In the setup, we attach the interrupts. Interrupt 0 is digital pin 2. Interrupt 1 is digital pin 3. And we're going to trigger the A rise subroutine and the B rise subroutine off of the rising edge of both of those. For now, this is just to get things rolling, okay? Because as you'll see, the code is sort of interlocked together. This is just to catch the initial start of everything. Okay, so then we start up the serial monitor. No big deal. The loop actually does nothing in this. We do all of everything we need to get position feedback from that encoder in the interrupts. Okay, so let's walk through this. And by the way, I couldn't find a good diagram of this, so I took a picture of my whiteboard. So you'll have to bear with me on that. So let's talk about this a little bit, and we have the interrupts triggering the rising event of either the A signal or the B signal. So let's start at point 0 and just walk through the code as if we're rotating through this, okay? So right now we're at 0. Let's say that the encoder is sitting at 0, 0, which would be somewhere out here, or basically right here, because this thing does repeat itself. So it would be right around here, 0, 0. So we start rotating it through, and we hit this point right here. The A signal goes from a 0 state to a rising state. And like I showed here, that does trigger an interrupt. And who cares which is which, A wire or B wire? You can always switch the wires on your board, but for now, let's just say that is the A wire. Okay, so we trigger the A rise subroutine here. The first thing we do is detach the interrupt on that pin, and I'll get to why this is important in a second. We make the A signal, which is just a variable. We change its value to a 1. So that's only going to be from a 0 to a 1 or go back to 0. No big deal there. And then we do a little bit of a figure. This is the direction detection part of the code. So if you look here, we check and see if the B signal is at 0 or if the B signal is at 1. So if you look here, right, we're right at this point here. We just changed state from a 0 to a 1, so meaning we're going this way. And that's all about change in time. So this time versus this time, what changed? The A signal went from a 0 to a 1, or a 0 to 5 volts. The B signal sits there at 0 volts. So if you look here, if B signal is 0, that means we're moving forward. So increment the pulses by 1. If the B signal is 1, then that means, so the A signal went from a 0 to a 1 while the B signal was a 1. That would have meant we're going this way, right? Change in time. From this time to this time, the A signal went from a 0 to a 1 while the B signal was high. That would have meant moving in reverse. And then we do a serial.print of the pulses and then reattach the interrupt, but this time we trigger it on a falling edge, and we trigger the A false subroutine, which is another separate subroutine here. And the reason I do this, and it's very important, I think in the code, and in my opinion this is the only way to do it, or that makes sense, is that if you miss a pulse, if you simply just do a change in state from either high to low or low to high, you have to trust your code that you'll catch each pulse. If you miss a pulse and you don't detect it, then there's a good chance that your counts will actually switch directions on you, which you don't want. That's the last thing you want. The worst thing that could happen in my code here is that you'll miss a pulse and you'll miss some resolution. That's it, because you'll catch it on the next pulse then. Alright, so anyways, this will make a little bit more sense as we go. So now, I mean, we know we're not going to rise again, basically, is what I'm saying. You know, we went from a 0 to 1. There's nowhere to go but down. You know, once you're at 5 volts, I mean, if suddenly you do start rotating it the other direction, it will fall. In the same way over here. So once you're up on the actual pulse, it will fall. So it makes sense to just reinitialize the interrupt on a falling edge. Okay, so anyways, let's continue walking through it. So now we went from a 0 to 1 while the B signal was low. We keep rotating it forward. All of a sudden we get a change in state on the B signal from 0 to 1. Okay, so if we go down to the code here, if you remember, we attached the interrupt to a B rise here. So we go down here, we now change the B signal from a 0 to a 1. Well, we detach the interrupt, the same exact thing we did in the A signal code. Then we do the direction detection. So let's see what happened here. We went from a 0 to 1 while the A signal was high, which means we're moving forward. So if A signal is equal to 1, we increment the pulses. If the A signal had been low while we went from a 0 to a 1, like right here, right? So if this was 0, so we went from a 0 to a 1 on the B signal, from this point to this point, while the A signal was low, that means we were moving in this direction, the reverse direction. So we were rotating it the other way. Right? So we would have decremented the pulses. So the same thing we do is serial.print of the pulses, and then we reattach the interrupt, this time on a B falling. So now if let's continue rotating it forward. So we're at this point here. Alright, we continue rotating. All of a sudden the A signal falls from a 5 volts to 0 volts while the B signal was high. So let's go to the A fall subroutine here. We detach the interrupt, make the A signal low or 0. The B signal was high, which means we're moving forward. If it had been 0, meaning we fell while the B signal was 0, that would have meant right at this point right here. So we went from 5 volts to 0 volts. I'm not showing it just because this thing repeats itself. So right here, this continues out like this. So this went from 5 volts to 0 volts while the B signal was low. That would have been going in this direction, reverse, the other way. Okay? So, of course, we then just reattach that interrupt to the rising edge. Again, no change there because we know that once we're low, it can only go up. Continue rotating through. Now the B signal changes from a high state to a 0 state. Okay, so we go to the B fall. Detach the interrupt, make the B signal low, do the direction detection. So if the A signal was 0, which it is, because we went from this state to this state while the A signal was low, meaning we're moving forward. If the A signal was high when we went from a high to low change, that would have meant we went from this to this. So we would have been moving in the reverse direction from this point to this point, okay? It's all about your change in time, where you're at in the waveform, if that makes sense. Okay? So the B falls. Same thing, we do the detection, the pulses, we print them out, and then we reattach the interrupt to a rising edge. And that is the entire code. And that will do this. I mean, it just tells you the position and counts it up. And like if you look at your initialization here of what these A signals, it really doesn't matter. Eventually it will figure out where it's at. So it'll kind of self-balance itself. So as simple as that. I wasn't really going to go into the processing code, but one more thing, about incremental encoders. It always starts at 0. So you're not getting your absolute position of the wheel, because on power down, I could be spinning this 100 times and it's power down. As soon as you power up, there's no way to know where the wheel is right now. So it's all incremental from where you last were, and that's how it figures it out. Okay, So I wasn't going to go into the processing code, but basically, I mean, this is pretty simple. I usually just copy this code out of other projects, but you know, basically we get that data in that I'm printing out, and we convert it into 0 to 360 because we know that 96 counts is equal to 360, or 48, half of that must equal pi, or 180 degrees, so 3.14, blah, blah, blah. And then we do the sine cosine of that, you know, wherever that angle is. And then we basically draw a line in the center of the screen with an angle at our rotational angle. So we make our set point equal to the sine and cosine value of that angle. Basically, that's how we do it, with a magnitude of the window. So, and then we do some color change. I'll put all this code up on the website, and you guys can hack at it if you want. It's just, I'm by no means a processing expert. So anyways, that is the encoder video. Hope that helps. Thanks.